The last lesson in Chapter 3 is 3.4, Applications of Polynomial Functions. So here we're going to use polynomial functions to model real-life situations. In the first example, it says the volume of air flowing into the lungs during one breath can be represented by the polynomial function v standing for volume at t standing for time, and here it is. Looks like it's a cubic function, right? And it's got a negative leading coefficient, and here it is graphed. The situation can be represented by the graph below. So we would be using some type of graphing technology to produce that. I can put it into Desmos and such. First question is, what does the x-axis represent? Well, the x-axis is the time in seconds. So you'll notice that even though it says x here, we could do x, or we could also do t because that was the graph of it. What does the y-axis represent? So the y-axis is the volume of air in the lungs, and the volume would be in liters. And actually I take a little bit of issue with the way this is stated here. It says the volume of air flowing into the lungs. It's not really flowing into the lungs. It should actually be the volume of air in the lungs. Okay, so it's not the rate of change. It's actually how much air is in the lungs. Determine any restrictions on the variables. Well, first of all, if the x-axis is time, we can't really have negative time. So I'm going to say that the t has to be greater than equal to 0. Anytime, no matter what this volume of air in the lungs is, we're not going to have negative time. And the second one I think we're going to have here is that we can't have a negative volume. So the volume has got to be greater than equal to 0. It's impossible to have a negative volume in your lungs. So let's look at this one over here. So let's consider when it's, here it says, using the graph, answer the following questions. Determine the maximum volume of air inhaled into the lungs. Well, the maximum would be right about here, and it's really hard to read that. So what I'll do is I'll just pop over and check up. Here's the graph on Desmos. So I typed that one in there, and here's the same one. So the volume would be that value right there. That would be the maximum, pardon me. So the first value would be your x, which is the time, and the second one would be the volume in liters. So I would put 1.168 for that one. And the second question is, how long for a complete breath? So this would be starting from 0, and I guess here you're exhaling, and then that's where it would be, the breath would be over. So I guess that would be 5.338 seconds. So I've written here the max volume at this time and the number of seconds it took for one complete breath. The last question would be, what percentage of the breath is spent inhaling? So you're inhaling going in, so from 0 to 3423 you're inhaling, and then you're exhaling, and the entire breath is 5.338. So I guess to answer that question, you're inhaling for 3.423 seconds, and the entire breath we said was 5.338 seconds. So that as a decimal, or that as a percentage, pardon me, would be I think around 64%. Okay, so I guess to apply this to other questions that you might get on a test or on the exam, it's the ability to say, okay, here is a polynomial and it's modeling something in real life. To think about the restrictions is probably the number one piece here. Is like, what makes sense? Where does the model stop working? And so how do I have to restrict either the x or the y value? Okay. Our second example could be very familiar for people here in Winnipeg. It says a block of snow measures 3 meters by 4 meters by 5 meters. The block melts in such a way that each dimension decreases in size at the same rate. At the end of a warm, sunny day, the block has a volume of 24 meters cubed. Draw the initial block of snow. So originally it is 3 by 4 by 5, but it has melted So each dimension has decreased at the same rate. So that is why we're subtracting the x from each amount. So in this case, x will be equal to the amount of decrease of each dimension. Okay, now we should write a polynomial function to represent this. Well, it's really been done for us right over here. So here is our polynomial, so we could just recopy it up there. And I guess the polynomial function, instead of doing the 24, we could say the volume of the box, which has shrunk x amount, would be equal to, and then we would write this 5 minus x, and then 4 minus x, and then 3 minus x. Okay, so we could write it that way, where v is equal to the volume of the box, and x equals, like I said up there. So we can define what our variables are. Before we go on, let's just think, are there any restrictions here? Is there anything that x cannot be? The smallest that x can be, like if x gets too large, I should say the largest that x could be is 3. So x has to be less than or equal to 3, because if it gets larger than 3, then it would have to be a negative dimension, and you really can't do that. Okay, and also I guess if the block was originally 3 by 4 by 5, x can't be less than 0, because we can't make the block bigger. So x has to be between 0 and 3. So that would be a restriction on the domain. If you pick something less than 0 for x, you'll have a larger block of snow, which you can't melt a larger block. If you have an x greater than 3, then you're going to be having a negative dimension. This side here, 3 minus x, would be less than 0. So that's thinking about how the polynomial function models or represents this situation. Now it says determine algebraically the new dimensions of the block. So it says that the volume is 24, so we start that way. Here's what we do. Well, I guess if it wasn't algebraically, if it was graphically, one thing you could do is you could graph this and graph like y equals that, and you could graph y equals 24 and see where the lines intersect and take the x value of that intersection. But if we're doing it algebraically, we multiply 5 minus x times 4 minus x times 3 minus x, and that's been done for us, so that saves us a little bit of work. And then we subtract 24 from both sides. So after the 24 has been subtracted from both sides, we get a positive 36 here, and we get a 0 on that side. Now, here is a long polynomial that we need to factor. And you'll notice, again, the work's been done for us just to speed things up. An a value of 1 worked, so x minus 1 is a factor, and then we get this negative x squared plus 11x minus 3. Now it's a little uncomfortable to look at that trinomial where that a value is negative, so what has been done from this line to this line here is you can see that a negative has been factored out of that trinomial. So the negative is brought out front, and this is turned positive, this is negative, and this is positive. So I guess at this point I'm wondering, is it possible to find more factors in that trinomial? And when I'm thinking, I guess I would need two numbers that multiply out to 36 and add up to negative 11. And I really don't see any that work here, because they would have to be different, and 3 and 12 don't work. 4 and 9 don't work, and things like that. So I think we got to bring out the old quadratic formula. So if you recall that if you have a trinomial in the form of ax squared plus bx plus c, and we want to find out the root, so we've put it into the form of 0, the possible x values are going to be, and this is on your formula sheet, so you don't have to have it memorized, but you should be able to invoke it or bring it into use when you've got a problem like this, is going to be equal to negative b plus or minus the square root of b squared minus 4ac all over 2a. So in this one here, it seems to me we have an a value of 1, a b value of -11, and a c value of 36. So I'm going to say that x is equal to negative, now my b is -11, plus or minus the square root of -11 squared minus 4, got to extend this a little bit, minus 4 times a times c, all over 2a. Now the most important part of this is this piece here, is that b squared minus 4ac. And if you recall, that piece there is known as the discriminant. It will tell us whether or not we have no real roots, 1 or 2 real roots. And so if I'm looking at this, I see that -11 squared is 121 minus 4 times 1 is 4. 4 times 36 is 144. 121 minus 44. So, we're going to have to square root it. We're going to get a negative value. What is it? In fact, it's -23. Can you find the square root of a negative value? No, you can't. So since the discriminant is negative, there are no real roots. Which is another way of saying, back over here, that we can't factor this anymore. Okay, so this is factored as much as we can. Okay, this is fully factored. If we were to graph this, the only place that it would cross the x-axis at x equals 1. So the only solution is x equals 1 from this factor right there, from that x equals 1. Now let's see, would it work if we put an x equals 1? So we can do a check here. Is 24 equal to 5 minus 1 times 4 minus 1 times 3 minus 1? This is 4 times 3 times 2. Sure, that works out just fine. Okay, so x equals 1 is a valid solution. So just to recall, a lot of the work in this question was done for us, but we had to do a little bit of effort ourselves to see if this last trinomial, if we could factor it any more fully. And if this discriminant had been positive, then we would have been able to get extract a couple more roots. And as long as it was within our domain, as long as the x value was between 0 and 3, there might have been more than one solution. All right, so let me see here. We've got another solution. But you know what I'm going to do? Instead of doing this solution here, I'm going to pick one that is from our an old provincial exam. So what I'd like you to do, we're going to ignore that page. What I'm going to get you to do is to copy this question down. So why don't you hit pause, copy it down, and then we'll talk about how to solve it. Okay, I've even added a little rectangular prism. So a box in the shape of a rectangular prism, oh, and it looks like I've lost a bit of a dimension here, is x and x plus 2 and x plus 10. So maybe I'll make this the longest side, can be x plus 10, and then maybe, I don't know, maybe this side will be x plus 2, and then this side will be x. So those are the different dimensions. This doesn't look very three-dimensionally to me, but at least it's something drawn. First of all, it says write a function. So there's really three things that we need to get done. First one would be over here, part 1, write a function v of x to express the volume, and then we need to find all possible values of x, given that the volume is 96 cubic centimeters, and then last, state the dimensions of the box. So the answer to the first one's pretty straightforward. We're going to say the volume Vx is going to be equal to, it's the product of those three sides, because the volume of this prism would be length times width times height. It doesn't matter what order I do it, I'm just going to say x multiplied by x plus 2 multiplied by x plus 10. Done, pretty easy. Now it says, find all possible values of x given that the volume of the box is 96. So I'm going to say 96 is equal to x times x plus 2 times x plus 10. Now we don't have a graphical means of graphing this and graphing y is equal to 96 and see where they meet, so we're going to be doing it algebraically. So what I need to do is multiply out the right hand side. So I think I'll multiply these two terms first. X plus 2 times x plus 10, that is x squared plus 12x plus 10, and then that gets multiplied by x, so I will get, and this is still equal to 96, and 96 there again, so now I'll get x cubed plus 12x squared plus 10x. Okay, so now to solve for x, like I've done before, I'm going to subtract 96 from both sides, so it's going to be equated to 0. So I get x cubed plus 12x squared plus 10x minus 96. Alright, so now is where the work comes in, where I have to say, okay, let's find some factors. Okay, the factors are all going to be, or the candidates are going to be factors of negative 96. So that's a lot of numbers. So, well, let's try it out here. I'll say, let's test for, my favorite one to start with is x minus 1, because I only have to put a 1 in there. So, actually not a v of 1, but maybe I'll call it a polynomial here, just to say. So, polynomial with 1 in there. So I will get a 1 cubed plus 12 times 1 squared plus 10 minus 96. That is definitely not going to be equal to 0. Okay, so let's try x plus 1. In which case I will get, I'll be putting in a negative 1, so I'll get negative 1 cubed plus 12 times negative 1 squared plus 10 times negative 1 minus 96. Alright, so I get negative 1 plus 12 minus 10 minus 96. Here I'll put p of minus 1 using this polynomial. So still you know what, that minus 96 is just a little bit too much for the other terms to handle. Let's try maybe x minus 2, in which case our a value would be p of 2, where I would get 2 cubed plus 12 times 2 squared plus 10 times 2 minus 96. 2 cubed is 8 plus 12 times 4 is 48 plus 20 minus 96. Oh, did I make a mistake here? This is supposed to be, let me just pause. Okay, I caught my error way back over here. I caught my error in my multiplying. It is a little too fast. This last term here is 20. I wonder how many of you were screaming at your monitor saying, you got that one wrong. So this should actually be 2 times 10 is 20. So this should be 20, so that should be 20, and still, however, if I make this 20, this is still not equal to 0. This turns into a minus 20, that's still not equal to 0. This, however, I was hoping it was going to work out. That 20 times 2 here is a 40, cool looking 4, and now let's see, 40 plus 48 plus 8 is actually 96, so minus 96 is 0. Yay! I got one. So in other words, x minus 2 is my first factor. Okay, so now let's use, maybe I'll go over here something. We'll use some synthetic division, and I'll take my original polynomial I had there. So I had 1 12, 20, and minus 96. And we're going to use synthetic division, and we're going to use a value of 2, and we'll see what we get here. So 1 comes down, times 2 over here. 12 and 2 is 14, times 2 is 28. These two added together make 48. Doubled is 96, and it's kind of a neat check. Good, it's 0, so that's 0. This 0 matches this 0. I get a remainder of 0. And so once I divide out that x minus 2, now I get an x squared plus 14x plus 48. So now if I want to factor this, see, I need two numbers that add up to 14 and multiply out to 48. I think 6 and 8 will work, because 6 times 8 is 48, and 6 plus 8 is equal to 14. So in other words, I've got my work done here. I've got x minus 2 times x plus 6 times x plus 8. Okay, when you sort of get to an end here, Bartlett, we should go and see exactly what we're trying to do here. It says, find all the possible values of x given that the volume is 96. So out of here, my possible values of x is x equals 2. Like, when would this be equal to 0, right? That's what we were working at. When x is 2, when x is equal to negative 6, and when x is equal to negative 8. But are all those values acceptable? Let me look. Here are the three dimensions, and remember, a length, a width, a height, each dimension has to be positive. So if I have a negative 6 and a negative 8, that would make definitely this one negative. So I'm going to say here, but x has to be greater than or equal to 0. So I'm going to reject this one. I'm going to reject that one. And I'll say, so x is equal to 2. Alright, so we got the answer for part B is find all possible values of x, given that the volume is 96. Now the last one is state the dimensions of the box. Okay, so I'll say the dimensions are, so if x is 2, it'll be 2, 4, and 12. So 2, and what were they? I think centimeters. 2 centimeters, 4 centimeters, and 12 centimeters. Okay, so that would be the last one. So this was definitely an answer. This was definitely an answer. And this was definitely an answer. Okay, for our three parts. So I'm just going to make it clear to the marker exactly what's going on. Okay, so we have sidestepped. We didn't do this question at all, which I think is okay. Let's go on to our last page, which is another one of a box one here. Here it says a box is assembled by cutting the corners of a piece of cardboard and then folding up the remaining sides. So what's happening here, here's the original piece, and this little X part here, that's taken out altogether. So now we're left with a funny looking shape, and this is where the folds are. So this part here folds up and makes a flap. And this part here gets folded up, and this part's here gets folded up. So if you can see now, this will be the base of my new a box. So this, I'll try to draw a line about that long. So this base is over here, this base is over there, and then we get a box made out of it. So it gets about, so big. I hope that makes sense to you. So it says the original piece of cardboard has a length of 30 centimeters. So 30 centimeters is this entire length. That whole length is 30 centimeters. And this whole width of the original piece of cardboard is 20 centimeters. And the square, which is cut out, is x long. So this, each one of these sides here, this is x. So x would be like this distance here, and also x would be this distance here. So each of these small little pieces here is x. Okay, so the first question, and you'll notice that you can't make x too big, because as x grows, this side here will be x, right? That dimension will get larger and larger, but the other sides shrink. Okay, write an algebraic expression that represents the volume of the box. Well, again, a volume is going to be equal to the length times the width times the height. It's going to be these three dimensions multiplied together. So one of those is going to be x. Right? That one's kind of easy to figure out. This x will be over there. But looking at this here, the length here won't be 30. And be careful, it's not 30 minus x. It's actually 30 minus 2x, because I have to take off an x from this side and I have to take off an x from that side. So the long dimension will be 30 minus 2x. And the height will be similarly, this one to here, it will be 20 minus 2x. All right, I hope that's sort of straightforward for you. And then it says, we would like a box. You know what, before I go on, let's just think about what the value of x could be. All these values have to be positive, right? So let's just think about a restriction here. X has to be positive, and also when we think 20 minus 2x has to be greater than or equal to 0. So in other words, minus 2x has to be greater than or equal to negative 20. So now when I divide both sides by negative, x has to be less than or equal to 10. So here x has to be greater than 0. So we know that x has to be between 0 and 10 in order for it to be positive. In fact, even maybe not even the equal signs, we could say, because we really shouldn't have a 0 volume of a box, so maybe we'll get rid of that one and get rid of that one. So x has to be somewhere between 0 and 10. All right, we would like to have a box with a volume of 1,000 cubic centimeters. Oh, well, here we go. 1,000 equals this, and so a lot of our work's been done for us. We subtract 1,000 from both sides, and from here to here, what was done? We've divided both sides by 4. And that's fair enough, because when we divide 0 by 4, it's still 0, and it makes everything simpler. So now we have a value of 1 out front here for our leading coefficient. They've already done a lot of work for us in that they've found out that x minus 5 is a factor, and then we have this one here again. So I think it's time to see, whether or not we can get two numbers that multiply out to 50 and that add up to negative 20. So I don't know, I don't think it's going to work easily. So why don't we bring out our quadratic equation again. We've got an a equals 1, a b equals minus 20, and a c is equal to 50. So first of all, our discriminant, you'll remember, is b squared minus 4ac. So let's just check that right away. If it's negative, we know that there's no real roots. So b is negative 20 squared minus 4 times a, which is 1, times c, which is 50. This is 400 minus 200. Oh, we should be good. Okay, so let's do the whole thing here. We're going to get x is equal to negative b plus or minus the square root of, well, 400 minus 200 is 200 all over 2a. So this is going to be equal to negative b, so negative 20, so I'll get 20 plus or minus the square root of 200 all divided by 2a. I'm going to get my calculator out here and figure this out. Alright, so using my calculator and figuring out both the positive and the negative there, I get x is equal to, I have two answers. One is 17.07 and the other one is that x is equal to 2.929. Now at the very end I'm thinking, okay, so I've got three different values that I can get. I've got these two, and plus I've got x equals 5 from this x minus 5 part over here. Looking back at my restrictions over here, I said that x needed to be between 0 and 10. So the only answers I could get is this answer here and that answer there. Okay, so here I've gone to my desmos.com and typed in this function, the 4x cubed business, and you'll notice I had to play a bit with the scaling. Check out that y, going by 500s there. But you can see that my only x values that I could take is between 0 and 10, and here is where it crosses. There's my 2.92, there was that value, and there is the 5. So those would be my two solutions. Okay, so this has been a bit of a longer one. I hope you do all right. So here is the homework, page 150. Try out those 4 different questions, and I'll see you in class.